Hi guys, in today's video we're going to talk about carboxylic acids. We've seen this group pop up a number of times already in our class, but we need to talk about the basic structure and properties of these. So what exactly is a carboxylic acid? Well, the general functional group can be drawn like this. Okay, so it's a carbonyl, C double bond O, that has an OH group attached and then some carbon-based group, some alkyl substituent. But let's actually take a little bit closer look at what this structure really looks like. And to do that, let's sort of zoom in on the structure. So if I were to redraw this in the following way, what we would see is that carbonyl, just like we saw with other carbonyls, has a pi bond and a sigma bond. All right, so this is the carbonyl carbon. There's the double bond, the sigma and the pi bond. And then we have this OH group attached. Now, one of the really interesting things about carboxylic acids is that this is an acidic proton. All right, and let's actually take a look at why that is. It actually has to do with the fact that this OH group is right next to this pi system, this pi bond. So I'm going to redraw this. Let's just actually use a real carboxylic acid. Let's use acetic acid. By the way, acetic acid is such a common acid, you really should know the name and structure of this one. It's the 2-carbon carboxylic acid. So it turns out that if you put this into water, the following acid-base reaction can occur. Water can simply pull off this proton, and when we do that, the electrons in the OH bond will then go reside on the oxygen, giving us this species, plus H3O+. Now this species is called a carboxylate. Okay, so we've converted the carboxylic acid, which has the OH on it, into this species, which is a carboxylate. It has an O-. So what is it again about the structure of this that makes this proton acidic? Well, it turns out that this carboxylate has an interesting and unique structure to it. Because these electrons are next door to a pi system in this O double bond, they can exhibit a phenomenon called resonance. Okay, and when we talk about resonance, we usually draw an arrow that has actually two heads on it like this. And what this is meant to indicate is that the electrons are actually going to be delocalized across several bonds. So if I push the electrons from this oxygen to this carbon, I'll make a double bond here. But then I'd have to break this one, and I'll push the electrons up onto that oxygen. So what you'd end up getting is the other resonance structure that would look like that. So notice now what's essentially happening is that this pair of electrons is now being spread over 3 carbons. And in general, that is a stabilizing influence. So the product of this reaction, the carboxylic acid going to this carboxylate, is stabilized by the fact that resonance can occur. And in general, for a reaction, if the products can be stabilized in some way, it will help to draw the equilibrium towards those products. That's what makes this type of proton acidic. So let's take a look at the actual equilibrium reaction and see if we can actually describe how the carboxylic acid looks when it actually deprotonates. So let's again use acetic acid as our example. And we're going to start to discuss a way to evaluate the strength of an acid. We're going to look at what's called the Ka value. So if I put this into water, we know that the carboxylate can be formed. okay, through this equilibrium reaction. Now, in this reaction, if I wanted to describe what's called the equilibrium of this reaction, we would describe it using what's called the equilibrium constant, or KEQ. Because this is an acid, we're going to call that a new type of KEQ called Ka. And Ka would be defined as the concentration of the products divided by the concentration of the starting materials. So we actually saw this, or you actually covered this in your general chemistry, looking at how to define the equilibrium constant. Again, this is a specific equilibrium constant for acids. So there's the concentration of my products. We have the carboxylate anion, which in this case is called acetate anion, and hydronium, H3O+. And that's going to be divided by the concentration of the starting material, which is our acid. All right. In general, the larger the Ka number, that would mean the more that the equilibrium lies to the right. Conversely, the smaller the Ka number, the more the equilibrium would lie to the left, or favoring the starting materials. While I have this up here, let me also just indicate that we're not only going to look at Ka values in our class, we also need to be able to look at a variation on Ka, which is called the pKa. And to calculate the pKa value, you simply take the Ka value and take the negative log of the Ka value. Now this negative sign is important, and notice that this is log base 10, log, not natural log, which is ln. So we're actually going to be evaluating the strength of acids using both of these types of descriptors, either the Ka value or the pKa. Ultimately, it's the pKa value that I really want you to get a good feel for. This is what organic chemists and biochemists tend to use much more often than the Ka values. So to get a feel of how to look at or evaluate these Ka and pKa values for carboxylic acids, let's just take a look at a couple simple examples. And I'm going to draw out the structure, and then we'll show what the actual values for these are. So for the first one, we're going to look at formic acid. This is actually a compound that's found in ant venom. Its structure is this. Next one we're going to look at is acetic acid. Okay, and then lastly, we're going to look at propanoic acid. Which has one extra carbon. So notice in this series, what I'm doing is I'm basically adding on a carbon on the side of the carbonyl. So actually, formic acid, you might say, well, that's not even really an acid, a carboxylic acid, because we defined a carboxylic acid as having a carbonyl and OH and some alkyl group. Well, this actually has a hydrogen instead of a carbon. So let's just look at what the Ka values of these are. So the first one here is 1.8 times 10 to the minus 4. The Ka value for acetic acid, 1.8 times 10 to the minus 5. And then lastly, 1.3 times 10 to the minus 5. Now these numbers are quite small. This would actually be listed out as 0.00018. This would be 0.00000. We have 4 O's in front of it, and then 18. So these numbers are very, very small, which means that these are very weak acids. They do not ionize, or they don't give up their proton that much. The equilibrium is actually favored towards the protonated form. So it can often be difficult to kind of compare these values that have these fairly large negative scientific exponents. So what we'll do then is we'll convert the Ka into the pKa. And again, to do that, you would just take the negative log of the Ka. So what does this become? Well, this one becomes 3.75 these two become 4.75 and 4.89. Now, what I want to tell you at this point is that we can now address which of these acids is a stronger acid and which is a weaker acid. So because the Ka value of formic acid is larger than these two, this one is actually the stronger of all these acids. Okay? So we have a trend in this series of increasing strength. So as we go from the bottom to the top for Ka values and also for our pKa values, we have this trend. So we can now make the following kind of conclusion for this. When it comes, let's actually not worry about too much about the pKa or the Kas. Let's look at the pKas. So in general, pKa, we can say that if larger pKa, okay, that means larger down here, this would be a weak acid. Okay, so large pKa numbers mean weak acid, whereas smaller pKa equals strong. Okay, because notice that as our pKa's are getting smaller here, that's actually a stronger acid. So in this series, formic acid would be the strongest acid, acetic acid would be kind of in the middle, and propanoic acid would be have the least strength in terms of giving up its proton. So we'll come back and we'll be using the pKa values a lot in this semester. This is just a brief introduction to the acidity of carboxylic acids. I hope that helps.